And now we have functions. Every day in our daily lives, we deal with functions in different ways, even though we don't actually treat those situations as functions. We actually deal with them very often. So what a function is an assignment from the elements of one set to an element of another set. You can also think about a function as a mapping between two sets, where you say the mapping of element A is element B in the other element X in the other set. So let's take a look at an example here. We have two sets, A and B. A is a set of students for a certain course. It's a finite set, okay? B is the possible grades they can get in the course. That is finite as well. It's a letter grade. So the function f is the mapping that you will have for every element of the set of students to the elements of the possible letter grades they can get. Another ways of representing a function is like this. Don't get confused with the implication symbol. So this is not an implication symbol, as we talked about in the previous chapter. You can also say f of a equals b, or use this notation as well. Or if the number of elements is not that big, you can enumerate one by one all the possible mappings that you have for your function. But there is one characteristic here that defines a function. As you can tell, not every student can get only one grade. Okay? Two students can get the same grade, but one student cannot get two different grades. This is a distinctive characteristic of a function. It means that for every element of A corresponds one and only one element in B. And for every element in A. So that means that no student is to be left without a grade. And it also means that every student gets exactly one grade, no more than one grade. You also observe from this example that element D was not mapped in the function. So that means that nobody got a D, but that's okay. This is still a function because every element on the left-hand side was assigned an element on the right-hand side. So keep that in mind. Now let's take a look at some definitions for functions. In the previous example with the Starfleet Academy course, we had that the set of students was the domain. You can also say DOM, right? DOM. And then the set of grades was the target or the codomain, right? And then the range or the image of that function, that particular function I show you with the students, was A, B, C, F. So the range or the image are the elements A, B, C, and F, not D. And D is not part of the image because D was not assigned to any students. Okay? So let's take a look at the formal definition here. The range of F is every an element on the right hand side, or an element of set B, such that B is a mapping for some element in A. Okay, good. Another definition is the one-to-one or injective function. A one-to-one function means that different elements of A get different images. So in our Starfleet Academy example, we don't have a one-to-one function. And the reason is that two students can get the same grade. So that's not a one-to-one function. Okay? Another definition is increasing functions. Or decreasing functions. So you have that if the function is going, if you look at the function in a graph where you have the x-axis and the y-axis, and then you see that the values, the corresponding values that map from x to y are increasing as the value of x increases, then that's an increasing function. Okay? If it increases every time, then the function is strictly increasing. If it plateaus for a while, then that's only an increasing function, but not strictly increasing. Let's see. We have another, this observation we'll see when we do the face-to-face synchronous session. We'll see that this observation holds. But for now, let's move on to definition number 7, and this is for onto or surjective functions. So those are functions where if we go back to our Starfleet Academy example, every possible grade was assigned to a student. Okay? In our example, we had that nobody failed. No, I think somebody failed, but nobody got a C. Let me see. Sorry, nobody got a D. So this function is not onto or surjective. The reason because D was not assigned to any student. Okay. So another definition, so we have the one-to-one, and then we have the onto, and the next one is one-to-one correspondence or bijection. So that means that the function is both one-to-one and onto. So don't confuse one-to-one correspondence with one-to-one. Those are two different things. If we look at the identity function, so the identity function, as you can guess, is the function that maps every element to itself. Okay? This identity function is one-to-one and is onto. If you visualize it, you see this is true. We have an exercise we'll do during the synchronous. And then we have inverse functions and compositions of functions. So let's talk about the inverse of a function. So we talk about functions as mappings, right? So functions can take you from set A to set B. The inverse of a function will take you from set B back to set A. but not all functions have inverses. The condition for a function to have an inverse is that it has to be a one-to-one correspondence, or a bijection. They are also called bijection. In our case here, with our Starfleet Academy example, we said before that this function is not one-to-one and is not onto. So, and this will show you why this is not invertible. There is no inverse to the function f. If you have element C, you don't know where to go back. Do you go back to Riker or do you go back to Worf? Okay. And something happens for D. For D, you just don't know where to go. There was no assignment of D. So this function is not invertible. So this takes importance in a number of fields. For example, in hash functions. I'm sure that you've heard about hash functions in cryptography. So hash functions map from two sets, from A to B. Those hash functions they are not necessarily one-to-one, and they are not necessarily onto. So there is no way to map back to the original set. The next definition that we have is the composition of functions. So that means that you can link together two functions, f and g. Okay? So that means that when you map from set A to set B, then you can also map to set Z. Okay? And the notation is this little circle symbol here. So the composition of G and F is denoted by that, and it means first you compute f of A, and the output of that function will become the input to G. Okay? Now, for these to hold, you need a few conditions. First, you need that the range of f be a subset of the domain of G. If you think about it and visualize the Starfleet Academy example, you probably know and visualize this. Also, the domain of f has to be equal to the domain of the composition of the two functions. Here we have the Starfleet Academy example. So we have the set of students, then we have the set of grades, and then we have the description of every grade. We're considering here that the Starfleet Academy are very strict, so to them a D or an F means inadequate, so they will fail with D or F. So the composition of F and G means that the composition of G and F means that first you compute F and then you compute G. Okay? The graphs of functions. We talk about the graphing the Cartesian product between two sets. So, and we talk about dimensions. Think about a two-dimensional space with the x-axis and the y-axis. So the graph of the function is the ordered pair remember the Cartesian product, A comma B, such that A belongs to A and f of A is equal to B. Okay? In this case, it's a Cartesian product on the same set. Could be from the same set if you have a Cartesian product of the elements of the integers, so you have that both sets are the same, right? And that's usually the case when you graph something or you have the real numbers x and y. But in this definition, it is generalized for two sets, A and B. So, two important functions to keep in mind are the floor function and the ceiling function. When you have a real number and you compute the floor of a real number, that is the largest integer that is less than or equal to that number x. So the floor of 3.1 is 3. The floor of 3 is 3. And the ceiling function. So the ceiling function, similarly, if you have the ceiling of 3.1 is 4, okay? The ceiling of 4 is 4, okay?